Hi, Physics 30s. I want to give you some overview on the notes that I just posted for electromagnetic radiation. And so I want to discuss the EMR spectrum briefly and also discuss the speed of light and then let you try a couple of practice questions on it. So a lot of my notes are coming from the studyphysics.ca website by Brent Klintberg. They're really, really good. So I've put his URL at the top. And let's just go through these. So electromagnetic radiation, it's made up of alternating electric fields and magnetic fields. Electromagnetic radiation is really energy that's being transferred for our purposes now. It's being transferred in the form of a wave, and the electric. What happens is you have a changing electric field that's going like this. I'm going to trace it here. Okay, so that's kind of going up and down. What happens is if you have a changing magnetic field like that, then that will induce a changing magnetic field at 90 degrees to that. In fact, you know what? I know I just switched colors, but it doesn't matter. So the B field will be going in and out of the page like this. Okay, if I could kind of loosely trace that. So those are going to be at 90 degrees to each other. And what's interesting is you'll see this later in terms of understanding electromagnetic radiation. Both of those are perpendicular to the direction of the wave. So the wave is going in, I'm tracing it here in purple. The wave's actually going that way. So what's really interesting about electromagnetic radiation is this happens actually in all directions. But if you're just looking kind of along one line, you'll have an electric field going up and down, a magnetic field in and out, and then the wave itself will propagate at 90 degrees. So everything is at 90 degrees to each other. What we know about electromagnetic radiation, it all travels at the same speed. It all travels at the speed of light, which is c. And you'll recognize that. That's in Einstein's famous equation, E equals mc squared. We're going to look at that later too. But c is the speed of light. And what we need to emphasize is that all electromagnetic radiation travels at that speed, not just light. So remember that. So for radio waves, for ultraviolet rays, or anything you might be considered like part of the spectrum, they all go that fast. Because electromagnetic radiation is considered to have wave properties, the universal wave equation applies. There it is right there. Velocity equals frequency times wavelength. But as you'll pick up here, we don't use velocity, we use the speed of light now. So we change that to a c. But it's still frequency times lambda. If you remember that from physics 20, lambda is wavelength. So it's the distance from crest to crest, trough to trough. And f is frequency, and it's measured in hertz. Or cycles per second. So if we come back to the spectrum, you might be familiar with a lot of these. The spectrum ranges from AC waves, which are way over here, low frequency AC waves, all the way up to gamma or cosmic waves. And these all travel at the speed of light. What's noted here, and I kind of added a couple of these, you have low frequency and big wavelength or large wavelength on the left side of the spectrum. As you move to the right, the frequency goes up. So the frequency gets really, really high by the time you get to the other side. And sorry, I crossed that out a little bit. But then you get smaller wavelengths. So it goes from, they kind of trade places, if you will. And there is an expression for that. We're going to learn that in the next chapter. That explains the energy of electromagnetic radiation. But for now, what we should add here, it is low energy here. Okay, so radio waves, AC waves, microwaves, those are low energy. As you make your way up, they get higher and higher energy. In fact, it gets to be dangerous to expose yourself to electromagnetic radiation. In fact, anything kind of above the, like, there's different kinds of ultraviolet light, but if you get above that, you get to a point where it's ionizing. So that just means there's enough energy in the radiation that it can rip electrons off of atoms and turn them into ions. So that's not good. It's not good for DNA. It messes up DNA. It's not good for a lot of things. So you can take some high energy radiation and it won't hurt you, but if you take too much of it over a long period of time, it can be bad. The wavelengths themselves, the radio waves, they can be huge. They can be like 100 meters long from crest to crest, trough to trough, and even bigger than that. But when you get to visible light, which is right in the middle, I like capturing the vocabulary here. We have Roy G. Biv, you remember that, red, orange, yellow, green, blue, indigo, violet. The infrared means before red, really. So before you get to red, you're in infrared. When you get past violet, it's ultraviolet, hence the names. You should know this range, and this is an approximate range. There is a little dispute over where exactly this range is, but I like to bookend it like this. I know you'll see even in the notes I'm giving you that a lot of references say that red is actually 700 nanometers or 750. So I like to remember it like this, though. The range for red, and this is actually here. Let me just back up. Let's just clear that out. This is for wavelength. And I'm going to say wavelength is approximately equal to 800 nanometers for red and then 400 nanometers for violet. Okay. And again, some textbooks will even they'll say that violet's 350. If you're between 8 to 400, you're going to be essentially in the visible range. That's approximate. That's just to help you remember it. The frequency range, though, is also, we're going to say, approximate, and it's in a sense reversed. And I had to add this here because it's actually 4 times 10 to the 8th hertz. Oh, no, I'm sorry, not 8th. That's the 14th. Sorry. 4 times 10 to the 14th hertz, or 8 times 10 to the 14th. Okay? So the wavelengths are getting smaller as you go from left to right, and the frequencies are getting higher. Hence the distinction we made earlier between high and low. I'm kind of circling extra stuff. So, but I'll come back to that visible range later. That one you should know. If you know that you're larger than visible light, then you're probably right in the infrared range. I'm not going to require that you memorize all of the ranges of each of these, but you definitely need to know the visible range. So you should, I kind of left these in the notes as well, which you can look at. There are some general things that you should know about the different kinds. So we start with low frequency alternating current waves. Heinrich Hertz actually did experiments with AC waves, and we name the unit of frequency after him because of his work with those. Radio waves, like I said, they run in the range. They're around 100 meters or plus or minus in terms of their length. You should make note of this. There are 2 different ranges of radio waves, and they're AM and FM. AM stands for amplitude modulation. What that means is you don't change the frequency, but you have a wave like this, and then you just increase the amplitude, and then you come back to the same. So the actual wavelength from crest to crest is the same, but what you modulate or change is the amplitude. So this is AM radio stations are in kilohertz, in terms like 10 to the 3rd cycles per second. And FM radio, or FM, is frequency modulation. So that's where you actually change the frequency. So you can have look something like this, and then you come back like this. Okay, so you actually are changing the wavelength. Because you change the wavelength, you're going to change the frequency. But FM stations are in megahertz. So that's 10 to the 6th cycles per second. Okay. Radar is also in that category, or it's I think it's before radio waves, but I might have that backwards. Anyway, so the next one is microwaves. Microwaves are actually in centimeters. So in terms of their wavelength size, in fact, that's why if you look at the door of a microwave oven, it has a whole bunch of, it's got a grid of a whole bunch of holes in it. Those holes are smaller than the wavelengths, than microwaves, the microwave wavelengths. So the microwaves can't escape. They bounce inside the microwave oven and they can't escape because they are bigger than those little tiny holes. And then, yes, if you open the door, the microwave thing shuts off, so you can't get, I guess you can't cook yourself really, unless you get inside the microwave. So don't try that at home. Anyway, so microwave ovens are clever that they match the natural resonant frequency of water, which is 2.4 gigahertz. So water naturally oscillates all by itself. It oscillates back and forth in terms of where the hydrogen atoms are located, kind of like an umbrella that's folding up and down, up and down. It's the kind of thing. And the using microwaves can actually heat up water. So that's really helpful. Anyway, I'm going to kind of blast through the rest of these. Infrared is just before. That's heat, of course, sensing heat. And we have infrared cameras. You're well aware of those. Sorry, my document duplicated things a little bit. Visible light. This is the spectrum. See here, it even says 700 nanometers to 350. I'm kind of pushing you to say 800 to 400 just to try and help you remember that. For all the math I'll give you, that range will work. But you don't need to know what each color is, but you should know the ends of red to violet. Ultraviolet, of course, is greater than that. So it's now, okay, obviously we're getting really, really small. We jumped from like centimeters. Now we're down to nanometers, okay? And it just gets smaller and smaller. X-rays, super high energy. That's why we wear vests when you get a dental X-ray, and technicians will leave the room. So, I mean, you can get some X-rays, but if you got a whole bunch, a lot, that could cause damage to your tissues. And then gamma is super, super high. Okay. So again, I kind of messed up here on the cosmic. So cosmic's even the highest, and you can get a lot of these high energy wavelengths from nuclear reactions, specifically from fusion and fission. The sun is a fusion reactor. And so it's pumping out tons of cosmic gamma and cosmic rays, which, by the way, we're shielded from that by our magnetic field and our atmosphere. And so we're not sitting on the surface of Earth getting pounded by cosmic and gamma rays. In fact, the only ones that are really making it to the Earth, as you know, are the ultraviolet rays. So I want to just touch on this aspect here. Initially, even in the days of Isaac Newton, actually Isaac Newton was convinced that light was a particle, that it was made of corpuscles, he called them. And his theory kind of was unchallenged until this guy shows up, Thomas Young. We're going to learn about his double slit experiment, which proved that light was a wave. But then as history continued on, eventually men like Albert Einstein and Max Planck, we're going to learn about them in chapter 14, they confirmed that light actually does have particle-like properties. And so the whole argument kind of came a little bit circular. And what we've currently concluded is that light has both particles. And you're going to see this as we go forward. We call it the wave-particle duality nature of light, and that it has actually both properties, which is just mind-blowing, but it's super fascinating. So at this point, I definitely want to mention this man, James Clerk Maxwell. He was a physicist, a brilliant mathematician. He actually was the one that did all the math to explain Michael Faraday's observations. And Maxwell predicted almost 100% accurately all the properties of light. And largely he did it before he died, which was interesting because his experiments or his projections were all validated by scientists that came after him. Famously, Albert Einstein had a picture of James Clerk Maxwell on his desk or something, or in his office, I don't know. But anyway, definitely an idol of Albert Einstein. So James Clerk Maxwell made these 5 predictions, and we're going to study all of them in this unit, or in this chapter. So his first one is electromagnetic is produced when a charged particle accelerates. So you have to take a charged particle and either accelerate it up and down a radio antenna or in any other means that you have. And if you do that, that creates a changing electric field, which induces a changing magnetic field. And so that produces, for the diagram that we already saw earlier, I guess I could race back to it, it produces this pattern of changing magnetic and electric fields. So the second one is that the frequency that you move that charge up and down with, I use the word jiggle there, highly scientific. The frequency that you do that will exactly match the frequency of the EMR produced. And so that's maybe not too surprising, but that's exactly how radio waves work. Actually, you accelerate electrons up and down an antenna at a certain rate. And you do that, if you do that at 630,000 times a second, that's 630 kilohertz, which is 630, it's AM 630 or 630 kilohertz. So the radiation will match that. Number 3, all EMR travels at the speed of light. We've already emphasized that. And Maxwell actually came close to predicting the actual number himself before he died. Number 4, we've emphasized this one. Both of the electric and magnetic fields are perpendicular to each other, and they're perpendicular to the direction of wave propagation. And then the last one, Maxwell predicted that electromagnetic radiation will do everything that a transverse wave does. And we are going to look at all 5 of these right away. Reflection, refraction, diffraction, interference, and polarization. So all 5 of those, we're going to cover those right away here in terms of our understanding of light. But for today, for the purposes of this video, we're just going to focus on the speed of light. So in your notes here, it shows a picture of Galileo. Galileo actually tried to determine the speed of light by taking a lantern that had a candle inside it, and he asked his assistant to go way far away from him on a mountainside with a lamp that also had a candle in it, and they had a cloth or something that they covered their lamps with. Galileo thought that he told his assistant, I'm going to uncover my lamp, and as soon as you see light from my lamp, you uncover yours. And I'm going to try to count or measure with time how much time elapses between when I open my lantern and when I see the light from yours. Okay, anyway, if you can imagine having that set up, anyway, it was completely inconclusive. Light travels so fast that, the instant Galileo opened his lamp, he would have seen the lamp from his assistant who was eagerly awaiting, and just way too fast. I'll show you another video in a minute of Ole Romer. He actually made a good observation about an eclipse of one of Jupiter's moons. And he used that. He came up with a really, really close estimation of the speed of light. The one that you need to know very well is Albert Michelson. So Albert Michelson, he was in the early 1900s, 1920s. He came up with a spinning mirror apparatus that let him accurately measure the speed of light. And this is the apparatus. Basically, he brought light in from a source. You see the light coming in here from the left, or from the right, sorry. And it hits an 8-sided mirror. He came up with an octagon mirror. So it hits this face, and then it travels a great distance and hits a parabolic curved mirror. And in this case, he set it up between 2 mountains. It was 35 kilometers away. It would hit this mirror and then come back and hit that side of the octagon mirror and then into an eyepiece or into observer. So then, so the observer could actually see the light that would have come from his source, which the source would have been over here. Okay. Now, that's great if you set that up, but then the trick is you start spinning the mirror. So Michelson started to spin this mirror at fantastic speeds because what he was trying to do was to get light to follow the same pathway, even though the mirror was spinning. And so the video that I'll show you hopefully will make more sense here, but he basically got this light to travel along this path And he did it so that initially when the light hit this face, so I'm going to color that in blue, the light would hit that face and then it would make its way to the curved mirror. But while the light was traveling, the mirror would actually rotate 1/8 of a turn. At least this is when it happened at first. So then the face that I just highlighted there would now have rotated to this position by the time that the light got back to hit the mirror. So basically, if maybe we should do it this way. If this was, here, let's make it a little bit bigger. If this was face A, and this was B, and this was C. So if those were the three faces, light would hit face A, and then while the light traveled, the mirror would rotate such that now A is here, B is here, and C is there. That's 1/8 of a rotation. Okay, so what Michelson found is with all that setup, he could actually determine the speed of light. So let's just do this example. He spun the mirror at, it was actually 32,000 RPM. That's rotations per minute. Okay. And the distance the light traveled, and what you have to watch for these questions is often you have to double the distance. Okay, because you're going to ignore this distance here and that distance there. Those are like, inconsequential compared to this 35 kilometers. So he went 35 kilometers this way and 35 back. So the distance would be 70, and I'm just going to deal with it right now. This is 70,000 meters, okay, that the light would have traveled. Now, I want you to see that the speed of light is a very simple calculation because it's a constant speed. So it's really the distance traveled divided by the time, and we're going to change this to c, but really we don't know what it is, so I'm just going to leave it as the speed of light. So the distance traveled by the light into this apparatus is the 70,000 meters. That's probably the easy part. But then the time is the tricky part. The time. How long did it take for the light to travel? Well, it's the time that it took for the mirror to rotate 1/8 of its period. Okay? So we need to find what the period is. I'm going to move over here. The period is equal to 1 divided by the frequency. Okay? The period is the time for the mirror to go all the way around once. The little catch here, and if you see RPMs, 32,000 RPMs, that's rotations per minute, and we need rotations per second. So what I'm going to do is let's take that 32,000. That's rotations per minute. And let's times that, or we're going to times it by 1 minute over 60 seconds. Basically, we're going to divide it by 60 seconds. And that's going to give us 533.33 cycles per second, or rotations per second, which you need to start getting used to. That is hertz. Okay. So that's, this is now the frequency that, or how many times the mirror rotates per second. Okay, that's amazing. It's just super fast. But anyway, the speeds are, we need that because light travels quickly. So what it means then is I can calculate the period. Now I've kind of done this a little bit in advance, but I'll show you. We basically need to go 1 divided by 533.33 hertz. And we get a period, very small, 1.875 times 10 to the -3 seconds. Now this is just the period. So students doing this, you need to make sure that you don't grab that number and then just use that for the time, because that's the time for the mirror to go all the way around once. And we only need 1/8 of that period because it's just barely, like it doesn't go all the way around once by the time the light comes back. So then all we have to do is take that time, and I like writing it like this. I'll say 1/8 of the period is equal to the time. Remember, period is big T, is equal to the time elapsed, or the time that we need. So we basically divide this by 8, and we get even a smaller number, 2.34. And you shouldn't round any of these right till you're all done. So that is the time, this -4 seconds. That time goes up here. And we can now calculate the speed of light based on our calculations. So if you go 70,000 divided by that time, we actually get 2.99 times 10 to the 8th meters per second. And this is exactly what Michelson figured out and how he calculated that. The actual speed of light, it's 2.997 something times 10 to the 8th meters per second. But as you'll see on your formula sheet, we never use the exact value. Not for our math, we don't have to be that precise. So we just use this number, 3.00 times 10 to the 8th meters per second. And whenever you're calculating the speed of light, using a Michelson mirror, sometimes you'll see in the question, sometimes they'll change the number of panels on the mirror. They'll say it's a 7-sided mirror, or a 12-sided mirror, or a 10-sided mirror. And so, based on that, all you're doing is you're just changing this right here. So it's, instead of an 8th, it would be a 7th, or it would be a 10th, or whatever. But I think you could handle calculating the speed of light. So these are the questions here that I'll let you work on. And I will post a short video that shows Ole Romer's method, because it's actually highlighted here in question number 3. And hopefully that helps you get started. So you can work on those questions, and I'll have some more stuff coming. Thanks.